Yes, thank you everyone for joining in. Shambhavi, please introduce the speaker, please.
Right. So today we have with us Diganta Misra. He serves as the founder and researcher at his lab, Landskape. They primarily work on computer vision, deep learning theory, and pruning, distillation as well. His areas of interest include abstract algebra, optimization, and mean field theory. Today we are going to discuss his paper on Mish, which is a self-regularized non-monotonic activation function, and the paper was submitted at BMVC 2020.
Go ahead, please go ahead. Thank you.
All right. Thank you, Shambhavi, for introducing me, and I'm really honored to get this opportunity to present my work. Before I start, I just have a quick question for organizers. So do we take like questions in between during the talk, or it's after the
It
presentation?
is left to you. It is left to you how you want to take it.
Okay,
do you want it in between?
I would prefer after the talk. So if I can get
sure,
all the
sure.
questions.
Yes. Yeah.
All right, great. So all right. Hi, everyone. My name is Diganta. As Shambhavi introduced me, I work as the founder and researcher at Landskape. I recently completed my undergrad in electronics with a minor in electrical. So this work is titled Mish, a self-regularized non-monotonic activation function. This was accepted as a paper at BMVC 2020 this year. So first of all, before starting, I would like to dedicate this work in the memory of my late grandfather who recently passed away, Professor Dr. Fakir Mohan Mish-A. So he holds a really huge place in my heart. Before I go in depth into the paper, I want to give a brief overview of what I'll be discussing today so that the audience is well familiar with what the prerequisites are and all the details that we'll be diving in later. So in this paper, we propose Mish, which is a novel self-regularized non-monotonic activation function, which can be mathematically defined as x into tan h of softness of x. In our experiments for the paper, we consistently observed that Mish helped improve information propagation with respect to network depth and improve the generalization strategy of a neural network due to its capabilities of making the loss landscape more smoothed and well conditioned. Since Mish is a novel combination of three other functions, which is identity, tanh, and softness, there's an increased trade-off between the training complexity of training neural networks with Mish versus training neural networks with ReLU. So we address this complexity by creating a custom implementation, which is based for GPU-based training called as Mish CUDA. This is available in code, and it's fairly easy to plug in and train your neural networks with Mish CUDA. So before I dive into the paper, I want to give a clear overview of where it all started with the motivation behind it and how one can take inspiration and get into this domain. This is a very exciting field, and there's a lot of recent works in it. For example, one of the recent papers that went to ECCV 2020 called as FRELU, or also called as funnel activation units, is also highly relevant to the domain of activation functions. So back in my second year during my undergraduate, I happened to have met a professor at my university. Back then, I wasn't even familiar with machine learning at all. I just knew they were really in hype. So I wanted to get into the domain, especially the mathematical side of it. And this professor, he in his chamber, he put forth a book from Cambridge publications in front of me and told me to open any page of the book and get any equation from that book, like in any page. So I picked one, and his first question was draw the function curve of that equation in paper. So there was some I could manage, some I couldn't, but he said, like, if you want to dive into the mathematical aspects of it, you should have the capability to visualize functions, especially draw them in paper, like how they look. So I think that's a very good intuition of having a great starting point into getting into nonlinear dynamics in neural networks. If you can visualize a lot of the mathematical aspects of what is going on under the hood, that really helps. So that's a brief overview and where it all started. And let's go more in depth. So activation functions, as known, are a very, very crucial component within any neural network architecture. And we know that the choice of activation functions do have adverse effect in the training capability of a neural network. So some activation functions are super cheap, super fast, like ReLU, which is very simple and easy to use and mostly works in all deep learning tasks. And there are some very dedicated activation functions which are used in specific tasks. Like, for example, Gaussian array linear units, also called as GELU, is popularly used in the GPT-2 architecture. So there's a lot of options available, but in this work, we'll try to look at what are some of the favorable properties that help in making an activation function more successful. So this is just a very brief overview of how activation functions are used in neural networks. As you can see by the formula, z equals to g of y, where g is basically the activation function mapping the linear transformation of the input to a nonlinear transformation. So as we know, activation functions, the main role of it is to introduce nonlinearity in a neural network. So as I previously said, there are a lot of options of using different activation functions for different tasks. And there's a whole dedicated Wikipedia page for all the different activation functions available with distinctive properties detailed. So we have some of the notable examples like Elish, ERELU, ELU, rectified ReLU, etc. Leaky ReLU also. However, ReLU over the years has remained the default choice for most practitioners and researchers because of obvious reasons, which is it's extremely simple to use, extremely low cost, and mostly works in all scenarios. But that doesn't mean that it doesn't have flaws. ReLU comes with a fair share of disadvantages. For example, because of not considering any negative information, because ReLU thresholds all negative information, it undergoes the issue called as dying ReLU, which is caused due to complete gradient information collapse due to the thresholding of the negative information. Also, we have observed that ReLU doesn't work as well as we might have expected in large neural networks where the depth is linearly increasing, and there's a collapse in the generalization capability of the neural network with ReLU at higher depth. This reasons have prompted into investigation of more smooth and continuously differentiable options like Swish and GELU, which have demonstrated a lot of success in varied tasks. So I show in this plot some of the very popular activation functions out there and the general layout. So the as you can see, the blue and the red curve, which represent Mish and Swish, are very closely related. However, there are some distinctive properties between them, which we'll get into later. So let's just discuss a bit into how Mish came into existence and what were the crucial factors that led to the development of a function. So Swish was discovered by neural architecture search-based approach, where they used a RNN-based controller in a conditional search space, which had a lot of nonlinearities within it. However, it didn't have a prior which included all the definitive properties that made Swish successful, like non-monotonicity, which is basically that the function curve is not increasing or decreasing at all points. And also that Swish has the ability to preserve small negative weights and has an extremely smooth profile and is very closely approximated to ReLU in the positive domain. So these were not the absolute conditions in the search space where Swish was discovered. It was also under a lot of debate that Swish and SILU, which is sigmoid inverse linear unit, also being closely related. So Swish can be formulated as x into sigmoid of x, where there is a small beta parameter within that sigmoid of x. So it's usually sigmoid of beta x, but in general practice, we keep that beta to be 1. However, in actual literature, that beta is a trainable parameter, while SILU is actually the default swish with beta equals to 1. So it is x into sigmoid of x. So Swish was a breakthrough into understanding activation functions, especially in the smooth domain and how they can improve generalization. However, they still didn't investigate properly into the definitive properties that made it so successful. Some of the recent work follow up to Swish paper, which includes smooth adversarial training, actually goes in depth into those properties, and we'll get into that a bit later. So based on those definitive crucial properties that helped Swish become so successful, we designed some candidate functions which can emulate those properties and probably improve the score on top of Swish. So some of those candidate functions that were chosen, you can see on the text in the slide, which are arctangent of x of plus of x, tan hypotenuse of x of plus of x log 1 plus arctangent of exponential of x log 1 plus tan hypotenuse exponential of x, and x tan h of plus of x. So just to give a clear understanding, soft plus is nothing but natural logarithm of 1 plus exponential of x, so which exists as another default activation function. So we take all these candidate functions and validate them on CFAR10 classification task with ResNet 20 backbone, and we run them for 3 runs each for 50 bucks. And from our experiments, we conclude that Mish, which is formalized as x tan h of soft plus of x, to be the best, most stable, and most well generalizing nonlinear activation function out of them all. So as you can see in the graph, we show the standard deviation of the validation accuracy curves across the 3 runs over the 50 bucks for those candidate functions. Although you can see the x log 1 plus tan h exponential of x to be a bit higher than that of Mish, we often saw that in most cases in other tasks, it had suffered gradient collapse. So that is why we explicitly say that Mish has the most stable performance out of them all. We don't show the curves of the remaining candidate functions because they had complete collapse and weren't able to learn at all. So finally, what is Mish? Mish is a smooth, self-regularized, non-monotonic activation function, mathematically defined as x tan h of soft plus of x. It has a lot of close similarities to that of Swish. For example, it uses the self-gating property used in Swish. So self-gating is basically you use the input, non-modulated input, along with a transformation of the input. So x into some transformation of x. So here the transformation of x is nothing but tan h of soft plus of x, while in Swish, the transformation is sigmoid of x. So other similarities with Swish includes it is unbounded in the positive domain, thus avoids saturation, which mostly slows down training because your gradient saturate, and it's also bounded below, which helps in propagating a small amount of negative information. And due to this preservation of the negative information, this tackles the dying ReLU problem, which completely thresholded the negative information. This essentially helps in better expressivity and information flow. There are a lot of questions regarding why we only take into consideration a small amount of negative weights and not more negative weights in the negative domain. The two plausible reasons that explain them is because weights usually learned are very small, and high weights which are encountered in case of neural networks, both in the positive domain and negative domain, are considered to be outliers. So we don't want to incorporate that information, and it's better to provide less weightage to them. So that is a motivation of keeping less amount of negative information in your activation. This is a probable differentiation between leaky ReLU and mesh or swish, because leaky ReLU is monotonically increasing in the negative domain. So it gives, it's linearly increasing in the negative domain, where that is encapsulated by a small factor, scalable factor of alpha, which is usually kept at 0.3 or 0.001. Uh, so that's an overview of what mesh is and how closely related it is to swish. As you can see in the plot, they are quite similar, and you can also see the point of difference between ReLU and that of mesh. I just want to make a quick remark over here. Although theoretically the function is unbounded in the positive domain, in practical implementation, the soft plus is bounded in the positive domain and has an upper cap of 20. We keep this so that we can provide numerical stability and not overshoot or have exploding gradients in our neural network. So theoretically, it is unbounded. However, in practical implementations, we keep an upper limit so that it provides numerical stability. Now, let's take a look at some hypotheses of why our activation function mesh might be performing better than that of swish. So here you see basically a good demonstration about the first derivative of mesh. So that's written in the formula over there. F dash of x equals to secant square of soft plus of x, x sigmoid of x plus f of x by x, where f of x is basically mesh. So as you can see, the x sigmoid of x essentially translates to that of swish, and the other remaining part, we formalize that to be an operator called as delta of x. So we hypothesize that this delta of x component to be acting as a preconditioner to give a prerequisite if people aren't aware in terms of convex optimization what preconditioners are. So preconditioners are certain types of components which are used in optimization problems to help make the landscape much more easier to optimize. So there is a complete dedicated section of study into precondition steepest descent. Those are the keywords that you would want to search on Google if you'd like to know more. So these are usually computed in terms of Hessians, which are very costly. So they help to make the loss landscape much smoother. So they improve the rate of convergence and make optimization much easier. So here we are hypothesizing that this delta x operator within the first derivative of mesh on top of swish is helping to make the loss landscape much smoother and easier to optimize as compared to swish, which actually will be somewhat confirmed, which I'll showcase in the later slides. Additionally, we also hypothesize that the symmetric nature of the derivative of mesh might also be responsible for easier optimization and gradient differentiation. So these are still not validated and still open to understanding, but these are some of the crucial hypotheses that we believe are underlying crucial factors in explaining why mesh performs better than swish. So as I said, regarding the delta x operator, we kind of see some of its effect probably over in this figure. This figure is essentially the output landscape of a randomly initialized 6-layered neural network. The left one shows the same neural network initialized with ReLU, and the right one shows the same neural network initialized with mesh. We keep the seed same, so the initialization point are same for both the networks. As you can see, the output landscape for ReLU is extremely sharp. There's a lot of rough transitions. However, that of mesh is very smooth, has a well-conditioned profile, and the output landscape can be related to that of the loss landscape of the neural network, and you can generally say that if the output landscape is smooth, then the loss landscape will also be smooth, and you'll be able to have easier optimization. So before I go to the further slides, I think there are a couple of questions, so I think it would be helpful if I can answer them.
Yeah,
okay, so
I had just a few questions.
yeah.
Yeah, I just wanted to know, when you mean negative info, you mean negative weight, right?
Yes. So the basically you're getting negative information means whatever input you're getting to the activation, that is negative. So like it's not weight, it's weight multiplied with the input. So
yeah, and yeah, you talked about this preconditioned steepest descent.
yes.
Can you give me an example of how is this helpful, or what is this exactly?
Yeah, sure. Just for preconditioned steepest descent, so we usually, as I said, use it in convex optimization problems where we want to make the loss landscape or the optimization landscape much smoother, and thus help in making the optimization process much faster. So there's
So
a
when you
dead.
say landscape smoother, what does that relate to in practical terms? When you say you want to make the landscape smoother?
So you mean like you can reduce the number of local minimas that you have. You can make the contour much smoother to traverse rather than
Okay.
having rough points where the gradient might be trapped and might not escape. So like
Understood. Understood.
it makes overall optimization much more smoother and easier. So I can like in like more mathematical terms is basically modifies the geometry of the objective function to increase the rate of convergence for gradient descent. So we know that gradient descent is essentially x k plus 1 step is equals to x k step minus eta k, which is the learning step, multiplied with the gradient or the nabla f of xk.
And this is, yeah, yeah. Go ahead, please go ahead.
Yeah, sorry. So in precondition gradient descent, we take a extra parameter called as hk, which is basically the symmetric positive definitive matrix, and we use that to modify our gradient descent steps so that the geometry of that objective function becomes much easier, and the rate of convergence essentially becomes much faster.
And this is specific to convex optimization?
From what I have studied, yes. I mean, I don't have much knowledge of whether
Okay.
this is used in other domains as well. But as I said, this is still a hypothesis and not confirmed.
Understood. Very good. Thank you. I think Chinmay has one question.
Yeah.
How exactly the symmetric nature of the derivative improve the performance? Will you touch upon it later in the presentation?
I think that goes into a bit more theoretical domain, and I can provide more references, but it would be a bit of out of
Okay.
scope for
Maybe you
this
can take it at the
discussion.
end. Yeah, yeah. Maybe you can
Yes.
take it, please.
All
Yeah,
right.
please go
So
ahead.
as we saw over here, the output landscape of the neural networks for case of Mish is much more smoother than that of ReLU, and this probably explains the effect of Mish in terms of how it makes optimization of the neural network much easier than in case of ReLU. So let's extend the work of output landscape to that of loss landscape. So in this, we basically visualize the actual loss landscape of neural networks, especially of a ResNet 20 trained on CIFAR 10 classification task using both Mish and ReLU. So as you can see in this visualization, Mish provides a much smoother, well-conditioned landscape with fewer local minimas, and thus makes optimization of the neural network much more easier. And also, as you can see in the top right visualization, the level of the minima of Mish is much lower than that of ReLU. That basically indicates that Mish obtained lower test loss than that of ReLU. So this kind of confirms our linkage from the output landscape onto the loss landscape of neural networks, especially when the activations are changed. We also extend this into the domain of Swish as well. So in this figure, we basically observe the loss landscape for Swish as well. The first, starting from the right, is Swish, followed by Mish, followed by ReLU. So as you can see, the output landscape for Swish is well conditioned as compared to ReLU, but still is steeper as compared to Mish. And Mish has a more wider minima, which actually helps in better generalization than that of Swish. So all these visualizations helps to understand the effect of nonlinear functions in neural networks, and essentially gives you a clear understanding of how they are helping to not only provide nonlinearity to the network, but also help to make the optimization landscape much easier and better to for the neural network to have a higher generalization capability. Just a final note that out of all the three networks, Mish still obtained the lowest test loss and the highest accuracy as compared to both Swish and Rel. So I would like to pause for a while so that I can show this cool animated video over here where we visually inspect the loss landscape, which I showed earlier. This was in collaboration with Javier IDME and Ajay from University of Illinois. So it's a very cool visualization. Let's just take a look. So as you can see upon visual inspection, the landscape of Mish looks much more well conditioned and easier to optimize than that of Swish and Relu. So it's just a cool visualization to have a confirmation on that. And this can be extended and for more architectures, which we will be doing in the future. All right, so those are more on the intuition side of why Mish works better and what are the possible reasons. Now we'll take a look into some ablation studies and empirical confirmation on the effect of Mish upon different hyperparameters of a neural network. So the first one that we'll look at is very important and extremely crucial in understanding the effect of activation, which is the effect of depth. So in this case, we basically take a neural network with increasing depth for MNIST classification. And as you can see at 15 layers, it's mostly Mish, Swish, and Relu are nearly at the same test accuracy. However, when we keep on increasing the layers, the accuracy for Relu drops very sharply, followed by that of Swish. But still, Mish is able to retain a good amount of generalization even at higher depth where both Swish and Relu are collapsing. So this kind of gives us a clear indication of why Mish works really well in more complex and deeper architectures, as we'll see in the benchmarks that I'll discuss later. One of the possible reasons of explaining this is you can basically visualize the rough gradient of a simple forward pass of a 50-layer network, and you'll see that the Swish gradient will collapse when you keep on increasing the layers at a linear fashion, while that of Mish will still have a non-zero gradient or at least a high gradient. So it still carries some information propagation capabilities, which probably explains why Mish still performs much better than that of Relu and of Swish at more increasing number of layers. Further, we also see the effect of different weight initialization strategies as shown over here. We take standard weight initialization strategies and in the same network setting, and we see that Mish consistently provides better accuracy than that of Swish for the weight initialization strategies that we experimented with. This is a very, very important domain, and I didn't touch upon it with more details because that would be a bit out of scope of this presentation. But if anyone is interested to understand more into the effect of weight initialization with that of activation, This is a main discussion in the field of mean field theory, which helps in explaining the effect of activation, effect of weight initialization, effect of depth in neural networks. So if anyone is interested, mean field theory would be a very good domain to start exploring into if you want to understand the effect of weight initialization and activation. All right, so we also do a standard experiment to see the robustness in terms of noise. So we add here increasing zero-centered additive Gaussian noise to the input data set, which in this case is MNIST. And we see that Mish consistently maintains a lower loss as compared to both Swish and Relu. Further on, we'll touch into more in terms of adversarial robustness. Here, the robustness generally means robustness to change in hyperparameters, but later on we'll see how mesh and especially normal smooth activation functions have effect into the adversarial robustness capability of neural networks. But before I go into the results, are there any follow-up questions until now?
Yeah, Diganta, I think you could repeat that field theory. I think that wasn't clear. You told you had to refer to something, right?
Yeah. So
I think like the which field theory or mean field theory? Okay.
Yeah, mean field theory. So I think the best references would be from papers from Surya Ganguly from Stanford or Samuels Coinhurst from Google Brain. Their works, and Jeffrey Pennington from Google Brain as well, they extensively worked on mean field theory. And I think probably the best paper to start with would be a paper titled as Deep Information Propagation. And also another paper titled as Resurrecting the Sigmoid. Both of these papers are authored by, I believe, Surya Ganguly and Samuels Coinhurst. So they would be a good starting point to understand the effect of weight initialization and activations in neural networks.
Okay, thank you. Yeah, please go ahead. There are no more questions.
All right, perfect. So, so to observe the statistical significance of training neural networks with mesh, we basically run a squeeze net with more than 10 different activation functions, including mesh for 23 runs, each of 50 epochs. And as you can see, mesh obtains the highest mean accuracy, second lowest mean loss, and third lowest standard deviation of accuracy. So kind of confirms that it is consistent across different architectures and different runs. In the repository, we do this same experiment, but for more than 20 activations. But for the scope of this, we only show the more widely used 13 activation functions. All right, so now onto the empirical evaluation. So we do benchmarks on CIFAR-10 classification tasks and on a variety of architectures, as you can see in the slide. And Mish consistently outperforms Swish and Relu in all of these architectures as shown. So this kind of empirically validates that Mish is able to provide consistent improvement in terms of accuracy for different variety of architectures. Further, we show results on ImageNet, which is considered to be a much more complex and difficult task as compared to that of CIFAR-10. And we compare here Relu, Leaky Relu, Swish, and Mish. We keep all the other network parameters and hyperparameters constant for fair comparison. And as you can see, we observe that Mish consistently outperforms both Leaky Relu and Relu, and in most cases performs better than that of Swish. Swish marginally beats Mish in the PiliNet architecture. However, as I discussed earlier, that Swish has a collapse in increasing depth. We kind of observe that in our large architecture of CSP ResNext 50, where Swish actually dropped accuracy from the baseline, which was 77.9, and it went down to 64.5. However, Mish actually improved accuracy by 1%. So This kind of gives a pivotal information into the effect of mesh, especially in more deeper architectures. And here in the second column where I have shown data augmentation, that basically means that we have used mix-up, mosaic, and label smoothing. We use this both for comparing the baseline and the network with mesh to observe that whether the effect of data augmentation is aligned with the performance boosts obtained by that of mesh. For more information on mix-up, mosaic, and label smoothing, I'll encourage the viewers to read the paper on YOLO v4, where all of this are discussed in extensive detail. All right, so we also observe some results on MS GOCO object detection task. This was with a more recent detector that was proposed at the YOLO v4. So we use the comparison between Liquid-ReLU and Mesh. So as you can see, Mesh consistently provides 1 to 2% improvement on the AP50 metric. These are not all of the MS COCO results that we obtain in our experiments. There are more additional results that are posted on the repositories, the links which are shown on the slide. All right, so as I had discussed at the start and during the overview, since Mish is a combination of 3 different activation functions, which include identity, tan, hypertenuous, and softness, because of this design, there is a trade-off between the accuracy boost obtained and the increased training complexity. So we address this by providing a custom CUDA-based implementation, which we name as Mesh CUDA. This is available for only GPU-based training and requires some prerequisite library installation to enable it to run. But as you can see, it heavily optimizes the performance complexity of Mesh and makes it much faster. You can see in the FP16 data type, Mesh CUDA is actually more faster in both forward pass and backward pass than native soft plus in PyTorch, although soft plus is an integral part of Mesh. So the code for Mesh CUDA can be accessed in the repository as shown, and all credits to Thomas Brandon from FastAI for helping me out on this. All right, so unlike most deep learning papers these days, which might have some complexity in implementing the architectures or the novelty in this paper, Mesh is super easy and easy to plug in and easy to validate and train on neural networks. In PyTorch, it essentially takes a couple of lines of code for you to define the activation function and plug it into your neural networks to use it as a general activation in place of ReLU or Liquid-ReLU. We do support other implementations for TensorFlow and Keras that can be accessed in the repository for Mesh. So concluding, we propose a novel activation function Mesh. We observe that the properties governing Mesh to provide a more favorable effect in the training dynamics of deep neural networks, which are also responsible for the improved generalization capabilities, like that include non-monotonicity, being smooth, and having the capability of conditioning the loss landscape to make optimization easier. The further work includes investigating more into the effects of the preconditioning effect that is induced by the delta X operator. And we plan also to reduce the complexity of Mesh by using the exponential equivalent for both tan-H and soft systems, and also to optimize it more for CPU-based runs rather than only GPU-based runs. So all the code and the pre-trained models are available on my official repository for Mesh, as shown in the slide. These are some of the references that I would encourage for the viewers to go through if they want to have a more in-depth understanding of nonlinear activation functions in neural networks. We do have some more slides to go through because I have kept them in the extras because these are not a part of the paper, and these are some additional experiments that were done out of scope of the paper and might provide some interesting information regarding the effect of activation functions. So as I touched upon earlier into the robustness, I didn't mention that later on we'll investigate into the adversarial robustness capability induced by smooth activation function. So in a recent paper by G et al. Titled Smooth Adversarial Training, the authors investigate the impact or the effect of different activation functions on the adversarial robustness capabilities of neural networks. And they observe a general trend that smooth activation functions not only provide a performance boost, but also improve the adversarial robustness of the network. And this property is also aligned with that of mesh. So as you can see in the graph, ReLU has a baseline accuracy of 68.8 with adversarial robustness of around 33.5%. But mesh provides not only a boost in accuracy, but also provides a boost in adversarial robustness. So does Swish and the smoother equivalent of ReLU, which is proposed as smooth ReLU. More details can be found in that paper by G et al. As shown in the slide. To make usage of mesh more easier, we support a lot of different packages which include mesh within the architecture, so that you can easily plug in and use them in your neural networks. The animation basically shows some of the very popular libraries and packages which have mesh inbuilt within them. So some of them include Darknet, TensorFlow, FastAI, OpenCV, Spacey, Hugging Face Transformers, TLib, and Deep Learning for Java. I wanted to show this, although this is not within the scope of the presentation. These are some visualizations that I was able to create using the candidate functions that I experimented with mesh. So they are more in the polar form. So I just wanted to say that it's not all about training or empirically evaluating our activation functions, but you can have fun with them. You can create artworks. So these are some of the fairly basic artworks that I was able to create from the candidate functions that I use while experimenting with mesh. All of them, including the code, is provided in my repository for this. And one more. Okay. So for more discussion, we do have a podcast episode that I would encourage for the viewers to listen to, hosted by Miklos, where we talk more in details about nonlinear dynamics in neural networks and specifically regarding mesh. This was recorded much earlier, so some of the details that you saw in this presentation today might not be discussed during that podcast, but I highly encourage to go through it so that you'll at least have a baseline understanding of what motivation was the inclining factor for me to go into this domain, and especially what lies ahead in nonlinear dynamics in neural networks. It's available in Apple Podcast and Spotify, and the link is in the slides. Right, thank you. That's all for me. I would like to take any questions if there is.
Thank you, Diganta. Very good presentation. Thank you very much. I had only a couple of questions. Is this applicable to time series forecasting problems or only computer vision problems?
Okay, great question. So I have received some similar questions like that, so including time series forecasting, natural language processing. So I haven't had the opportunity to extensively evaluate mesh in more different domains like that of time series forecasting. I do have some very basic NLP benchmarks. However, they don't provide a clear indication on which activation function proves to be better, maybe because I haven't done large scale evaluation. So it's up to the users. I think there are a lot of different use cases that I have come across recently regarding mesh that I didn't even start to consider during my benchmarking. For example, one of them was used, I believe, in depth estimation. So although that is a computer vision based task, but it's not a classical task like that of image classification or object detection. So one depth estimation was one. Normalizing flows was also another one. Another one was a obtaining the volumetric occlusions in 3D volumetric data. That was recently accepted to the IEEE VIS conference. That was a paper by some researchers at University in Finland, I believe. And the very interesting use cases that I have come across recently that do suggest that this can be used in more tasks than that of classical computer vision, but I really don't have a clear conclusive answer to suggest that it works better than other activation functions. So up to use.
But yeah, for computer vision, it is exceeding the benchmarks. Yeah.
Yeah.
So I have one last question before we go to Chinmay.
Yeah.
Can you go to the backward past the time table 6?
Yeah.
Yeah. What I wanted to ask was, if I compare generally, I'm asking in general, if I compare two different architecture. So when I'm trying to compare the resources, I think you had used the term computational overhead in the paper.
Yeah.
So how would I do that when I have two different architectures? I'm just using two architectures to test the performance. And if I have to present computational overhead, how would I go about doing that?
So I think one crucial components to investigate upon computational overhead for different architectures or different methods in general would be to understand memory complexity. So for some reason, some papers don't discuss about it, some papers do discuss about it. Example, one of the Google paper called as I think standalone vision model, standalone self-attention vision models that basically try to replace standard convolution layers in neural networks with attention-based layer. Although it reduces parameter complexity and flop complexity, it still has a higher memory cost because you create more overhead tensors. So to be honest, most of the cost is not from the functional implementation, is most from the data loading and the data storing in the location bits and memory, and that mostly comprises, like for example, usually we profile after some sort of warm-up time, because that warm-up time takes to allocate some sort of memory in the cluster where you're benchmarking. So one of them is very important, I think we should understand, is memory complexity. There are a lot of inline profilers available for PyTorch and TensorFlow to profile your memory complexity of your code, so you can essentially get the runtime and the storage memory complexity of any neural network or a method. So I think one of them is a library called as MEMLab, MEMLAB, that is available for PyTorch. So you can basically get to understand the memory complexity. For runtime complexity, it becomes very difficult because most of the papers are benchmarking different GPU-based architectures, and they have a lot of moving variables, so it becomes really difficult to have like a constant benchmark. Only if you have a dedicated architecture or a dedicated GPU that you're benchmarking on, then it becomes easier. And here the forward pass and backward pass was more relevant because we were not comparing neural networks, more specifically we were comparing different activation functions. So we wanted to see the forward pass, which is basically the x tan s of plus of x, and the backward pass, which is the gradient computation of that function. So we don't have to do forward pass and backward pass for networks.
What I was getting to at is, let's say I am working on time series forecasting problem. And if let's say you're the reviewer and I have compared two different architectures, apart from all the regular accuracy, if I have to present computational overhead, does it make sense to do that? Or as a reviewer, do you really look for that numerics, or is it worthwhile doing that?
Right. I think for any top conferences, reviewers, I think more inclined towards comparing different methods or different architectures in terms of parameters and flops. Like those are considered to be, I believe, standard metrics for complexity. So we usually compare, let's say, ResNet with DenseNet. We compare them in terms of flops and parameters. There are other points of comparison as well, but as I said, the other points of comparison kind of have a lot of moving variables that you need to keep constant to have a fair comparison. So in that case, parameters and flops become the main metrics for comparison for computational overhead.
Okay. Thank you. Thank you. Chinmay, please go ahead with your question. Chinmay.
Hello.
Yeah. We can hear you. Go ahead.
So yeah, first of all, excellent presentation, Diganta. And well, I wanted to ask, is there any specific tool to visualize the loss landscape that you showed in your presentation?
Oh yes. So there's a repository by Tom Goldstein called as Lost Landscape, I believe. It was also a NeurIPS 2018 paper, I believe. The paper is titled as Visualizing Lost Landscape of Neural Networks. So its corresponding repository is that. So we use that as our standard for visualizing lost landscapes. However, the artistic representations that you saw in my slides were a bit different than the ones generated by that repository, and mostly Javier, who helped us generated those landscape using his tools. So I'm not really aware of what exact tools he used, but yeah, we use that repository as a like starting point for visualizing lost landscape.
Okay, can you please say the name of the repository again?
I think it's so the username is Tom Goldstein, and the repository is called, I think, Lost Landscape. It's I believe on my repository in my references section, so I think that should be easily accessible.
I think I got it in the group chat.
All right, perfect.
Yeah, thank you so much.
Thank you.
Yeah. Shambhavi, please go ahead.
So yeah, I would like to know, like, yeah, people come up with interesting names for their papers. Why Mish was chosen as the name for the function?
Interesting question. In fact, when I applied Mish paper to a conference, I got one reviewer who actually asked me the same, like why the name Mish. There is nothing special about it actually. So in fact, the first name that I had proposed for this was FONLAF, FONLAAF, Fast Optimized Nonlinear Adaptive Activation Function. That was the acronym. It was a terrible name because it's not at all fast, like until we had created Mish-A. So so after that, actually, a person very close to me actually told me to name it Mish because I was inspired by Swish, and that's it. I didn't really much think about it much, to be honest.
Also, was like when you submitted the paper, were there any follow-up comments or iterative comments from the reviewers? If yes, what were the changes made to the initial structure to get it accepted?
Yeah, so that's a really good question. So so some of the comments were the following. So as you can see in this table, some of the benchmarks for Swish are missing because I had to do all the experiments on my own computational resources, and I obviously didn't have that much of computational resources to support my experiments. So in my first submission, ResNet 1850 and SpineNet 49 wasn't available. So I did that after the comments posted by the reviewers that they would like to have more comparison between Swish and Mish for more different architectures. So that was one of the comments that I received. The other comment that I received was actually for the loss landscape. So in my first initial submission, we hadn't submitted the loss landscape visualization. We had only submitted the output landscape. So, and we had said that output landscape being smoother also suggests that loss landscape will be smoother and thus promote easier generalization. But the reviewers wanted to actually have a visual confirmation on that. So based on that, we, after quite a lot of effort, we are able to get these visualizations that we also presented in the paper. Other than that, we did have like some like structural changes to the paper, not more in terms of intuition level, but the reviewers do have a strong suggestion upon investigating more into the delta X operator, and especially finding a more optimal solution. Like I don't think Mish is like probably, I won't say the best activation function or the most optimal activation function. I think that this basically is an investigative confirmation into the properties that make activation functions successful, and there can be other activation functions which use the same properties and can be more cheaper and much better than Mish. So their suggestion was to just not like keep close the chapter over here, but also investigate more into those properties and find a more optimal solution which is more like cost friendly in terms of computational, because we still haven't optimized Mish-A to the extent that we would want. Like it's still slower than Relu. Obviously, making it as fast as Relu would require a lot of effort, because Relu is so simple and it's really unimaginable that you can make them equal in cost. But we still haven't even optimized this for CPU. So there are a lot of factors that needs to be investigated upon further. And as one of the viewers suggested in the questions, which was, have you tried other tasks like time series visualization? So I think those are also interesting to see whether Mish pulls out in other different tasks rather than only in computer vision. Because one of the papers that was accepted at ACL 2018, right after Swish was published, the title of that paper is called "Is It Time to Swish?" And that basically did a complete thorough benchmarking of Swish in NLP tasks. So they said that, okay, Swish proposed and it works really well in computer vision, but does it also work in NLP? So I think we have to investigate more into understanding what can be an optimal solution for different tasks as well. So yeah, those were probably the more notable follow-ups from the reviewers.
Diganta, thank you. Can you just go to that profile, that smooth profile? I just want to know how to interpret that figure where you have two different plots.
This one?
No. Before this? Yeah, this, the next, just go to next, where you have the next.
Oh.
Yeah. How to interpret these two plots? Can you just shed some light?
So so you basically, to plot the output landscape, all you essentially do is like visualize this graph, like individual graph as a grid, and you pass in all the grid locations of the coordinates to the neural networks, and the neural network proposes a magnitude for that grid.
Okay.
So
that has been plotted against what? There is the output after that.
So this is like you have a randomly initialized neural network, and you basically pass in the grid coordinates, and it basically gives a magnitude. That's essentially it. So it's the output landscape. It is not like correlated to the optimization of the neural network. It's basically how if a randomly initialized neural network is taken, how its output landscape will generally look like. So the very rough abstract understanding, because we hadn't when we had done the visualization of output landscape, we hadn't completed the loss landscape visualization. So we didn't have this like visual confirmation that also translates to loss landscape. So that was a more abstract understanding of the effect of activation function. I think this is also inspired by one of the figures in the Swish paper, which can be accessed. It's on the Swish paper, like I think the second version of it, where they also plot the output landscape of randomly initialized neural network. So I think it can be, more details can be found in that to have a more clear understanding. But the code to generate this is on my repository if anyone wants to play around with it or try it out.
Thank you. Please go ahead, Shambhu.
you said regarding Swish, that people extended it to measure a performance between all the architectures using Swish, do you plan to extend Mish to NLP tasks as well?
Um, well, I would like to be honest, but I'm not really well familiar in NLP domain, so I would obviously have to do some reading and get into pace to get started with benchmarking mesh. I would also encourage like people to also try it out on their own. Like I think not just NLP, like other domains as well, as I said. So yeah, I would definitely be inclined towards understanding that, but I think right now I'm more inclined towards understanding like effective activation functions in perspective of edge of chaos, which is closely related to the mean field theory. So that would give more of a theoretical understanding of activation functions rather than just an empirical evaluation from doing NLP benchmarks or time series based benchmarks.
Great, thanks.
Yeah, I think Chinmay had one question. I think you'll address at the end about the symmetric nature of the derivative of Mish to improve the performance. Is there any
Yes.
resources?
So um, I haven't come across much literature, but like from general experiments of my own, I have kind of seen that symmetric derivatives which promote having a symmetric gradient is actually a bit helpful in neural network training. And I don't have a clear conclusion. As I said, this slide was mostly regarding hypotheses. I really don't have a clear conclusion that that is a factor, but it might be, like, because I observe a general trend. So I'm still investigating into it. I think once I have more details from some of my findings, I'll be able to provide a conclusive comment. But I believe if one is interested into this preconditioning edge of chaos or the gradient effect or induced by activation functions, it would be really helpful to read mean field theory in general, and I think that would be a prerequisite to have more clear understanding of this.
Okay. Chinmay, any follow-up question, Chinmay?
No, sir.
Okay, thank you very much. Yeah, do you have any, Swarup, any questions? Okay. Oh. Yeah, I just had one question, I think, from the paper itself.
Yeah.
Yeah, you use multi-step learning rate. Any comment on that, or why you used multi-step?
Multi-step learning rate, I believe that is corresponding to the ImageNet section in the paper. That's default in ImageNet benchmarking. So we usually do 100 epochs with multi-step learning of reducing the learning rate by like 0.1 at every 30 epoch steps. So we have first drop in 30th epoch, the second drop at 60th, and the third drop at 90th. So that's used in standard benchmarking practices. So a follow-up comment on that would be, I still do believe that there are better hyperparameters that can be plugged into the network to facilitate more performance boost than the one we are getting with just using mesh, because networks are essentially networks are designed to facilitate the maximization of performance improvement proposed by each individual components within that neural network. However, as I stated in my ImageNet benchmarking, we kept all the parameters and hyperparameters constant between the network that had ReLU, that had leaky ReLU, that had Swish and mesh. So I believe if we do like a better hyperparameter search to improve the hyperparameters for mesh exclusively, we might even get better performance boost. This has been, in fact, investigated a bit by the FastAI team, where I believe Les Wright and I keep forgetting the name, but some of the other people from FastAI who used Mesh along with, instead of using SGD, they used Ranger Optimizer, and they used a combination of both along with, I think, one cyclic learning rate policy to beat 12 fast AI benchmarks on the ImageNet and ImageWoof dataset. So yeah, I do think that if you can combine Mish with some other improved hyperparameters, which especially will help to boost performance, you can get even better performance gains than just using Mish in a vanilla architecture.
Yeah. Thank you, Diganta. Thank you for your time. Yeah. Yeah, I think there are no more questions. Thank you very much, Diganta. Balapriya, do you have any question? You can unmute yourself and go ahead if you have any. Okay. Thank you very much, Diganta. Thank you for your time. Very, very good paper. Lots of interesting results. And how long did it take for the experiments?
I won't say it's over, but I started off with the idea. I believe that was April 2018. Yeah, April 2018. So it took me around 1.5 years, or somewhat like that, to have a conclusive repository with all the results. But I do owe to many people who helped me throughout the project, and like there were countless of them, so I can't like say all the names, but yeah, it wouldn't have been possible to get to this place without all of their combined efforts.
Yeah. Very well written, and very well presented. Yeah, thank you. That's it from me. Shambhavi.
That's it.
Yeah.
Thank you so much.
Thank you for your time, Diganta. I am also want to test this for time series, but I think there are some limitations, but I'll find out once I dig deeper. But yeah, because I am dealing with time series forecasting issue, so some algorithms which are used in computer vision are not directly applicable in that. We're trying to solve that. But thank you very much for your time. We greatly appreciate it. Thank you very much.
Thank you for having me. Thank you. Bye-bye.